Prescribe the degree 6.
Thank you. It's working, right? So thank you very much, and thank you to the organizers for this very enjoyable conference. So I will be talking about maps, and because I've only got 20 minutes, let me just skip the introduction and rely on Gregory's lecture for this. So just to be precise, by map I mean planar map, which are also rooted and only bipartite. And what I'm interested in here are scaling limits of these maps. So for this, as Gregory mentioned yesterday, we will view maps as compact metric measured spaces just by looking at a vertex set equipped with the graph distance and also the uniform probability measure, as we discussed also with Wendelin's question. And all the limits will be in the sense of the Gromov-Hausdorff-Prokhorov topology that I will not define. But if really you don't have any idea what that is, well, a corollary of this is that you get convergence of any metrics of distances between any well, uniformly random vertices. Okay, if you sample k uniformly random vertices and you look at the metrics of the pairwise distances, you have a limit object for this. So basically we want to consider a sequence of maps with the size tending to infinity, rescale the graph distance by something tending to 0 appropriately, and look for a continuum object. And we want to do this for random maps. So another way to define a map is as a gluing of polygons. You can imagine that you have a finite list of polygons that you glue together by identifying the size 2 by 2 in order to create a surface that has the topology of the sphere. And then you just read off the graph like this. And because we view everything up to homeomorphisms, there are really only finitely many ways to glue your polygons in order to get a sphere. So from this, it's very natural, if you want to sample a random map, let's keep this, to start with a deterministic list of polygons and just take one of the possible gluings uniformly at random. So you can formalize this in that way. For every n, we are given n integers, dn1 up to dnn, say ranked like this, and we just sample a uniformly random map with n faces and degrees given by the 2 dni's in order to have a bipartite map. So a very particular example that was mentioned by Gregory in his first lecture is when all the dni's are equal to some fixed p. In this case, for every n, what you glue are just n copies of a 2p gone, and you get a 2p angulation. And the most studied case is p equals 2, which are called quadrangulations. Okay, is the model clear? Okay, I guess so. So let me just briefly review what we know about 2p angulations. 3 breakthrough papers. First one by Jean-François Le Gall, who showed that in this case, whatever p, you should rescale the map by n to the 1/4. Well, we knew you should, but he showed that if you do that, then your sequence is tight, in the sense that from any sequence of integers, you can always extract a subsequence along which your maps converge, viewed again as a metric measured space. And then if you want to show convergence of your sequence, you just need to show that all these subsequential limits are the same. And it took him several more years, and Gregory found a different argument at the same time for quadrangulations. And now we know that these maps converge. And let me just, if you look at the scaling factor, you can forget about the 9/4, which doesn't matter here. And you have this p minus 1n for 2p angulation. Maybe it's a bit small. That you raise to the power 1/4. And if you include the p in the scaling factor, then the limit is universal. It's the same for every model, and that's what we call the Brownian map. Okay, so maybe that's what the Brownian map looks like. Don't know, it's very informative. Actually, this is a large random quadrangulation where colors indicate distances to a uniformly chosen point, which is the V star in Gregory's lecture. And for some reason, blue means close and red means far. Okay, good. So that's what happens when you glue n copies of a given polygon. Now, for the more general model, when the polygons may vary with n, and even at n fixed, we can glue together different polygons. An important quantity will be this sigma n square, which is just the sum of the dni minus 1, and which is exactly this pp minus 1 n for 2p angulations. So the main theorem I would like to discuss is the following. First, that if you rescale the map by square root sigma n, so this thing to the 1/4, then you're always tight. Without any assumption on the degrees, basically the fact that the map is uniformly sampled given these degrees spreads out the faces well enough, and nothing terrible may happen. So this recovers the case of 2p angulations, but for 2p angulations we know that not only they are tight, but they actually converge throughout this Brownian map object. And here again, this map converges to the Brownian map as soon as dn1, which is the largest degree, is small compared to sigma n, so square root of this. So just a few words about this assumption. You see, the point is, if you take a face in your map, say it has degree 2d, and you look at the diameter of this face, so the greatest distance in the whole map between 2 points on that face, then typically this distance is of order square root d. I'll come back to that later. But so this assumption means that at the scaling square root sigma n, you have no macroscopic face. All the diameter of the faces will go to 0. And so what this theorem says is that if you have no macroscopic face, then you get the Brownian map at the limit automatically. All right. So now we fully recover the case of 2p angulations, because this is always much greater than p square. But this is always much greater than p square when p is fixed, but even when p is not fixed. You see? P could vary with n. This is always true. So actually we can get a more general result, and for any pn, whatever its behavior, if you take a 2pn angulation with n faces, you always get the Brownian map at the limit. Just if pn goes to infinity very fast, you have to take a very strong scaling factor. So this question was raised to me by Gregory a few years ago, and apparently it answers a question of Eric Fusy.
So is this the strongest statement you would expect to be true for prescribed degree sequences?
Yes. I mean, it depends what kind of statement you're looking at. But maybe the next slide will answer your question, the last point of the next slide. Let me make a few more comments about this result. First, this is work in progress and very recent. Originally, I thought about discussing a previous work where I look at this model in the particular case where sigma n square is of order n, which I call the finite variance regime, because if you divide this by n, this really looks like a variance. And there are also annoying technical assumptions. I mean, not just this, but also more assumptions. Also, Gregory discussed a case of stable Boltzmann maps yesterday that you can see as a particular case of this, because just look at the definition of the Boltzmann measure. It only it only involves the degrees of the faces and not the way they are glued together. So basically, you can view a Boltzmann map as a map where the degrees are random but conditional on the degrees. The map is uniformly chosen among the maps with these degrees. And for the case of Boltzmann maps with a, well, in the domain of attraction of a stable law, no, doesn't matter. Also, the Boltzmann measure has a product form. It's a product of all faces of Q of the half degree of the face. So that means that basically your degrees are just IID. So in the end, a Boltzmann map, you can just view it as you sample random degrees according to some common distribution, and then given these degrees, you glue them uniformly at random to form a sphere. And if the common law belongs to the domain of attraction of a stable law, well, that gives you tightness of these maps in any case. And if this stable law is a Gaussian law, actually you can check this, this no macroscopic face assumption, and you get convergence to the Brownian map. So it's slightly more general than what Gregory said yesterday in the finite variance case. You also have the infinite variance but Gaussian case. Okay, just another comment. Gregory also discussed convergence towards Brownian disk. When you have maps with the boundaries, you can just view it as a particular case of this, when dn1, the largest degree, will be your boundary. So in this case, you're not in the case where you have no macroscopic face. If you have only one macroscopic face, then you get this Brownian disk object. And if the face is really large, you can even get a Brownian tree, but I will not discuss this. And so maybe to answer Scott's question, this is work in progress, and the reason why it's work in progress is that the theorem says if you have no macroscopic face, then you get the Brownian map, and I strongly believe that this is an if and only if, that if you have a macroscopic face, there's no way you can get the Brownian map at the limit. And I used to think that this was the easy part of the if and only if statement, but I haven't been able just to really spot the correct argument for the moment. I strongly believe it's true. All right, let me briefly say a few words about the proof. As yesterday, the proof relies on a bijection with labeled trees. So for this, you need to distinguish a uniformly random point in your map, and then you can just encode your map with this kind of object. So it's a genealogical tree where each vertex has a label. And if you remember the bijection, the leaves of the tree are in bijection with the vertices of the map, different from that one, and labels up to a shift, because we want the root of the tree to have label 0, but up to this shift, labels just gives you the distances in the map of the vertices to this particular point. And so then to understand the behavior of this map, you just need to understand the behavior of this tree. And actually, it has a very nice distribution. So the leaves are in bijection with the vertices of the map, and the internal vertices are in bijection with the faces. And we have seen that their number of children is half the degree of the face. So actually, in this tree, you have n internal vertices, and their number of children are the DNIs. And the tree is just uniformly chosen among all the possibilities. And then given the tree, the labels are obtained by putting the root at 0 and using this local rule at every branch point, where labels evolve like a bridge. And this bridge converges to the Brownian bridge, and this is where you get this, this square root d here. All right, now to talk about scaling of label tree, the easiest way is just to encode them by path, because we really know how to deal with path. So in red, I number the vertices according to the depth first search order, like Igor did yesterday. And the paths are called the height process here and the label process below. And it's very easy, just at time k, you look what is the vertex number k, say here 10. In the first path, you put the generation of the vertex, so just its height. And the second, you put its label. And so the height process encodes the geometry of the tree, and the label process encodes the labels. And we are interested in limits of these objects. So the continuum analogs probably you know that if you replace the height process by a Brownian excursion, well, probably you know it for the contour function, but it's almost the same. If you replace it by a Brownian excursion, you get a Brownian tree. And the analog of the label process was this process Z that Gregory briefly mentioned, called the head of the Brownian snake, which encodes similarly Brownian labels on the Brownian tree. So every point of the Brownian tree has a label, and along a branch they evolve like standard Brownian motion, and at every branch point they just split and continue independently. So here labels again are indicated by colors, red for the high values and blue for the low values. And similarly to the discrete setting, this label tree, or more precisely this pair of functions, encodes your Brownian map. And again, don't forget that this process actually records distances to a uniformly chosen point, which is somewhere here. Okay, and so finally, to get convergence of maps, we really reduce the problem to a problem of limits of path. And actually, amongst these two, this one is important. This one really records distances to a uniformly chosen point, but distances anyway. So this is really the one you want to understand. And to be more precise, what Jean-François proved is that if you show tightness of the label process, then you can obtain tightness of the maps. Because, okay, the label process again encodes distances to a uniformly chosen point, but using the triangle inequality in a clever way, that gives you an upper bound for distances between any 2 points. So if you can control this label process, you can control distances between any 2 points, and that gives you tightness, more or less. And then if you want convergence to a Brownian map or a Brownian disk, then you need to show really convergence of this label process to the continuum limit. And the point I wanted to make is that in order to show the tightness of the label process, you don't need a tight control on the tree. In particular, you don't need to understand very well the height process. The proof of the tightness only involves the Lukasiewicz path of the tree that Igor mentioned yesterday. And the Lukasiewicz path is a really simple process. So Igor was looking at Bien-Aimé Galton-Watson trees, which correspond to Boltzmann planar map. And in this case, the Lukasiewicz path is just an excursion of a random walk with only positive jumps, not less than -1. So it's a very simple object. Here it's not a random walk, but it's a process with exchangeable increments. And it's very easy to control, and that's why we can obtain tightness of maps without any assumption at all on the degree. And so this gives you tightness of maps, and if you want convergence, say, to the Brownian map, you need to show that the label process converges to the head of the snake, the Brownian snake. And for this, what you look at are just finite dimensional marginals. And here you need the finite dimensional marginals of the height process. So here you need to show that the height process converges to a Brownian excursion, but only in the weak sense of finite dimensional marginals. So really the point is you don't need tightness of the height process. And I will finish with this. Actually, I don't know that the height process of the tree is tight. So we have seen that the tree without the labels has a very, very explicit distribution and very interesting. You just give first you just give yourself the child sequence, and then you just sample a random tree uniformly at random among those with this child sequence. And well, this was studied by Nicolas Broutin and Jean-François Marquer in this finite variance regime, and again with some other annoying technical assumption, and they prove that the height process converges to the Brownian excursion really as a continuous function, and so they get convergence to the Brownian tree. But in this more general setting, for the moment, I have no idea. Maybe it's not even true that it converges to the Brownian tree in this general setting. So, yeah, we stop with this very nice conclusion. Thank you.
Questions?
Well, that's an obvious question. Do you, what is missing to deal with the non-bipartite case?
what is missing to deal with a non-partite bipartite case is a nice tree. You see, really, the fact that tightness is very easy here is really due to the use of the Janssen-Stephenson bijection. It was not so easy with the Boutier-Di Francesco-Gitter bijection. And now, for the moment, we have the Boutier-Di Francesco-Gitter bijection for non-bipartite maps, but it's a really ugly tree. You know it. But there is some hope because Sigurdo is working on a bijection to reduce the Boutier-Di Francesco-Gitter bijection in the non-bipartite case, and I have a look at it. But it's really a technical problem.
Okay, let's thank the speaker again.
Thank you.